Let's consider k vectors b1, b2, bk in Rn. As an example, let's say we have 3, 2, 1, and negative 1, 1, 1, and these are vectors in R3. Then in this case, we have k equal to 2 vectors in R3. We're going to say that in general, these k vectors are linearly independent, are linearly independent if the only solution of the equation x1 b1 plus x2 b2 plus xk bk equal to 0, 0, 0 is x1 equals 0, x2 equals 0, xk equals 0. Then this is the definition for k vectors to be linearly independent. Let's see if these vectors are linearly independent. Then, according to this definition, we need to check this equation, x1, 3, 2, 1, plus x2, negative 1, 1, 1, equal to 0, 0, 0. And then we need to decide if the only solution of this equation is 0, 0, 0. Notice that we end up, when we do the operation, we get 3x1 minus x2. Here we get 2x1 plus x2. And here we get x1 plus x2 equals 0, 0, 0. And therefore, we end up with this system. 3x1 minus x2 equals 0. 2x1 plus x2 equals 0. x1 plus x2 equals 0. That means that when we want to decide if k vectors are linearly independent, we end up analyzing a homogeneous system. We can check that the augmented matrix of that system is going to be 3, negative 1, 0, 2, 1, 0, 1, 1, 0. And this matrix is row equivalent. The reduced echelon form of that matrix is 1, 0, 0, 0, 1, 0, 0, 0, 0, which means that this system is equivalent to the system x1 equals 0, x2 equals 0. And therefore, we have that the only solution of this equation is x1 equals 0 and x2 equals 0. And then, according to the definition, this is the definition, of linearly independent. According to the definition, these vectors are linearly independent. And these vectors are linearly independent. We will write Li, linearly independent. What we did here, it can be done in general to check if some vectors are linearly independent or not. What do we have? We have k vectors, b1 equal to, let's say, b11, b12, b1n, and bk is going to be bk1, bk2, bkn, then when we set up the system, when we set up this system of equations, we end up with this homogeneous system. X1 B11 plus xk bk1 equals 0, and here x1 b1n plus xk bkn equals 0. That means that we just need to solve this homogeneous equation, and if the only solution is the solution 0, 0, 0, 0, then we get that the vectors are linearly independent. Otherwise, the vectors are not linearly independent. Let's do another example. Let's check if the vectors 1, 2, and 2, 4 are linearly independent or not. And the question is, are these vectors linearly independent? And then we need to set up the system. x1, 1, 2 plus x2, 2, 4 equal to 0, 0. And then here we have x1 plus 2x2, 2x1 plus 4x2 equal to 0, 0. And then we end up with the system x1 plus 2x2 equals 0, 2x1 plus 4x2 equals 0. You see, this is the system compared. This is the v11, v12, v21, v22, and then these two systems are essentially the same. And then in this case, when we do the augmented matrix, we end up, this is the augmented matrix. And we can check that this is row equivalent to the matrix 1, 2, 0, 0, 0, 0. This is the reduced echelon form matrix of that. And then that means that the system reduces to the system x1 plus 2x2 equals 0 and 0 equals 0. Here this is a good system. That means that x2 is a free variable. And as we pointed out before, anytime we have a free variable, that means that there are infinitely many solutions. And then we conclude that these two vectors are not linearly independent. Then the question is, are these vectors linearly independent? And the answer is, no, they are not. 1, 2, and 2, 4 are not linearly independent. When vectors are not linearly independent, they are called linearly dependent. Let's see some theorems that help us to decide when some vectors are linearly independent. Notice that when you think about solving this system, that means solving this system, essentially what you are finding is you are finding the null of a matrix. The null of what matrix? In this case, you are finding the null of the matrix 1, 2, 2, 4. Notice that the null of this matrix, by definition, is the solution of this system. That means that if we have k vectors and we wonder if they are linearly independent or not, then with this notation, we need to check if this matrix, the matrix B11, B1n, B21, B2n, BK1, BKn, we need to check if this matrix has null equal to the 0 vector or not. Then let me write it as a theorem. Theorem B1 equal to B11, B1n. and bk equal to bk1, bkn are linearly independent if and only if the matrix A has null of A equal to the zero vector. Then essentially, if we have k vectors, then we need to compute the null of a matrix to decide if those vectors are linearly independent. What matrix? The matrix that you get by making the columns of that matrix equal to the vectors that you are trying to find out if they are linearly independent or not. Let me do another example like this. Say example. Let's see, are the vectors 1, 2, 3, 4, and 1, negative 1 linearly independent? And let's use this theorem. Then essentially we need to consider the matrix A equal to 1, 2, 3, 4, 1, negative 1, and then we need to compute the null of that matrix. But the null of that matrix is the solution of this system, x1 plus 3x2 plus x3 equals 0. And then we have 2x1 plus 4x2 minus x3 equals 0. And then when you do row reduction, if you consider this matrix, actually when you do the row reduction of this matrix, you get the matrix 1, 0, 0, 0, 1, 0. And that means that in this case, the system that is equivalent to this matrix is the system x1 equals 0 and x2 equals 0. Let's see this system. This is a good system. What are the basic variables? Basic variables are x1 and x2. And what are the free variables? In this case, x free variables is x3. Notice that we started with 3 variables. x3 is a free variable. And since we have a free variable, that means that the null of this matrix is not the set with only the 0 vector. And therefore, these vectors are linearly dependent. They are linearly dependent. Actually, we have a theorem from before that says that anytime you have a homogeneous system and there are more variables than equations, then the system has infinitely many solutions. And the reason is because when you do the homogeneous, when you do the augmented matrix and you reduce, there is always going to be free variables because there are more variables than equations. Then let me write that as a theorem. Theorem. We have B1, Bk are vectors in Rn, and k is bigger than n. In this case, we have 3 vectors in R2, and 3 is bigger than 2, and that's the reason that these vectors are linearly dependent. Then here in general, if we have k vectors in Rn, but k is bigger than n, then the vectors are linearly independent. Then, as an example, if we have like 3, 2, 1, 4, 0, 2, 3, negative 1, 7, and 1, negative 1, 4. And we wonder if they are linearly independent or not. Then we can say that these vectors, let me just write it as a set, are linearly dependent. And remember that the reason that is behind this is because when you want to analyze if the vectors are linearly independent or not, then you end up solving this system. 3x1 plus 4x2 plus 3x3 plus x4 equals 0. 2x1 minus x3 minus x4 equals 0. And x1 plus 2x2 plus 7x3 plus 4x4 equals 0. And when you analyze this, when you do row reduction, you know that for sure you will get a free variables, because the number of pivots, the most you can have is 3, and you have 4 variables, and then one of those columns is going to be without a pivot. That means that one of these variables is going to be a free variable. And since there is a free variable, then the solution of this equation, if we call this B1, B2, B3, and B4, the solution of the equation x1 b1 plus x2 b2 plus x3 b3 plus x4 b4 equal to 0. This equation has infinitely many solutions, because when you think about that equation like this, there is a free variables. That means that there are infinitely solutions. Remember, being linearly independent, it means that the only solution of this equation is x1 equals 0, x2 equals 0, x3 equals 0, x4 equals 0. Something that is interesting to point out is that if you have one vector is a multiple of the other, let's say if we consider 3, 7, and 9, 21. If we consider these two vectors, then I can say that they are linearly dependent. Then they say these vectors are linearly dependent. And in order to check this, we go back to the definition. Notice that one is a multiple of the other. In this case, we have in particular that 921 is 3 times 3, 7, right? And therefore, this means that 3 times 3, 7 minus, or let's say plus negative 1 times 921 is equal to 0, 0. But when you think about the equation x1, 3, 7 plus x2, 921 equal to 0, 0, then we get that this equation has a non-trivial solution. Precisely, we have x1 equal 3, x2 equal negative 1. We have found a solution of this equation which is not the solution 0, 0, and therefore these two vectors are not linearly independent. That means that they are linearly dependent. Actually, we can generalize if we consider the set B1, BK, and somehow we know that one of the vectors, let's say the last one, B sub k, it doesn't have to be the last one, but let's just write in this term, if the last one is a linear combination of the others, let's say is lambda 1 B1 plus lambda k minus 1 BK minus 1, then this set, let's call this set S, then the set S with these k vectors is linearly dependent. And the reason is that when we think about this equation, I can rewrite this equation like lambda 1 b1 plus lambda k minus 1 bk minus 1 minus bk equal to the zero vector. But that means that if I consider this equation x1 b1 plus xk bk equal to 0, 0, 0, this equation above, this equation provides a solution of the equation of this one. We make x1 equal lambda 1, x2 equal lambda 2, and xk minus 1 equal lambda k minus 1, and xk equal negative 1. This is a solution of this equation, but notice that this solution is not the zero solution. Why is not the trivial solution? Because xk is negative 1. Remember that the trivial solution is x1 equals 0, x2 equals 0, sk minus 1 equals 0, sk equals 0. But you see this part? This is negative 1. That means that the whole thing is not all equals 0. And then we have found a solution of this equation, which is not the trivial one. And therefore, these vectors are not linearly independent. That means that they are linearly dependent. Then if you see something like 1, 2, 3, negative 1, 2, 1, and the vector, let's say 0, 4, 4. Notice that this one is the sum of these two. Then, because of this theorem, I can say that this set is linearly dependent. Let me summarize what we have seen so far. Then first, we have that a collection of vectors v equal to b11, b1n, and bk equal to bk1, bkn are linearly independent if the only solution of the equation is of the equation x1 b1 plus xk bk equals to 0, 0 is x1 equal to x2 equal to xk. And then we have seen that this is equivalent to, when you set up this system, you end up with this system. B x1 b11 plus xk bk1 equals 0, and x1 b1n plus xk bkn equals 0. It's a system of equation with n equations and k variables. Then being linearly independent means that this system of equation has 0, 0, 0 as the only solution. Then this provides an easy way to decide if k vectors are linearly independent, because we just set up the system of equations. We do row reduced. If we have a computer, we have a calculator, we can easily do the row we can easily find the reduced echelon form, and then we can solve this system. And if we see that there is a free variable, that means that the solution has infinitely many elements, and then we can say that they are linearly dependent. But when there is no free variable, then the solution is this, and therefore the vectors are linearly independent. We also have that this is equivalent to say that the null of the matrix that we get by placing the vectors B1 as the first column, and then the vector B2 as the second column, and the last vector BK1, BKN is just the set 0, 0, 0. Remember that the null of a matrix is just the solution of this homogeneous system. Okay, then we have this. And some consequence that comes from this. We have a theorem that if K is bigger than N, then the vectors B1, BK are linearly dependent. The reason is because if K is bigger than N, this system has more variables than equations, and any homogeneous system with more variables than equations has infinitely many solutions, and for that reason the solution set is not going to be just 0, 0, 0. Okay, then we have this theorem. Also, we have that if some V sub I is a linear combination of the other vectors, then the whole set B1, BK is linearly dependent. And the reason is because when this happens, when we have that one of them is a linear combination of the others, then we can find a solution of this equation which is different from the solution this equals 0. Actually, this is an if and only if. If the vectors B1, BK are linearly dependent, then for some I, V sub I is a linear combination of the others. Let's do an example. If we consider these three vectors, and if we want to check if they are linearly dependent or independent, then we need to solve this system. x1 plus 2x2 minus 3x3 equals 0. Negative x1 minus 2x2 plus 4x3 equals 0. x3 equals 0, and 7x1 plus 14x2 minus 25x3 equals 0. When we do the augmented matrix, we get that augmented matrix is 2, 1, negative 3, 0, negative 1, negative 2, 4, 0, 0, 0, 1, 0, 7, 14, negative 25, 0. And the row reduce And the reduced echelon form of this matrix is the matrix 1, 2, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and 0, 0, 0, 0. That means that this system is equivalent to the system x1 plus 2x2 equals 0, x3 equals 0. Notice that this is a good system, and we have that the basic variables are x1 and x3, and the free variable is x2. But since we have a free variable, we know that the solution of this system is going to have infinitely many solutions, and for that we have that these vectors are linearly dependent. And we're writing this linearly dependent. Let's see this part of the theorem. This theorem says that when you have a collection of linearly dependent vectors, then one of the vectors can be written as a linear combination of the others. In order to do that, we need to solve the system. Let's solve the system. Let's see, x2, x3 is 0, and that means that x1 should be negative 2x2, and x3 should be 0. And then we can pick x2 equal 1. Let's pick x2 something different from 0. Let's pick x2 equal 1. If we pick x2 equal 1, then we get that x1 is negative 2 and x3 equals 0. That means that the vector x1b1 plus x2b2 plus x3b3 is the vector 0, 0, 0, 0. If we select this combination, that means that b1, x1 is negative 2, negative 2b1 plus b2 plus 0b3 is the vector 0, 0, 0, 0. Let's check this. I'm saying that negative 2 times the vector 1, negative 1, 0, 7, plus the vector v2, 2, negative 2, 0, 14. This is the vector 0, 0, 0, 0. Is this true? Negative 2 plus 2 is 0. Negative 2 times negative 1 is positive 2 minus 2 is 0. Negative 2 times 7 is negative 14 plus 14 is 0. But from here, look what you get. When you solve for v2, you get that v2 is 2 times b1. And that means that I can pick I equal to 2, and it's a linear combination. This v sub 2 is a linear combination of the others. I can write that v2 is 2 times b1 plus 0 times b3 if we want. Then we have written one of the vector as a linear combination of the others. Since I want to ask about this, let's practice more problems of this type. Let's consider the following example. Let's decide if these vectors are linearly independent. Then we need to analyze the following system. x1 minus x2 minus 4x3 equals 0. 2x1 plus 3x2 plus 27x3 equals 0. 3x1 minus 5x2 minus 26x3 equals 0. Then this system has augmented matrix 1, negative 1, negative 4, and 0, 2, 3, 27, and 0, 3, negative 5, negative 26, and 0. Notice that essentially this matrix, the first 3 columns, the vectors that we are considering, and the last column is 0 because this is a homogeneous system. And this matrix has a reduced echelon form matrix, which is this one. Therefore, this system is equivalent to the system x1 plus 3x3 equals 0 and x2 plus 7x3 equals 0. Notice that the basic variables here are x1 and x2. These are the basic. And the free variable is x3. Since we have a free variable, then we can conclude that these vectors are linearly dependent. But then, in order to write one vector as a linear combination of the others, we can select the free variable, one of the free variables. If there are many, you can just pick one of them to be 1 and the rest equals 0 if you want. But then when you pick x3 equal 1, what do I get? I get that x1 is equal to -3 and x2 is -7. And therefore, that means that x1 b1 plus x2 b2 plus x3 b3 is the vector 0, 0, 0. But with this choice, we have that -3 times b1 minus 7 times b2 plus 1 times b3 is the 0 vector. Let's call this the 0 vector. And from here we can solve for b3. We have that b3 is 3 times b1 plus 7 times b2. Let's check if this is true. When we have b3 is the vector -4, 27, -26, and the claim is that this is equal to 3 times b1, 1, 2, 3, and then plus 7 times -1, 3, -5. Then when we have that the collection of vectors is linearly dependent, then we have that one of the vectors can be written as a linear combination of the others. We also have the other implication. If we already know that one of the vectors is a linear combination of the others, then the collection of vectors is linearly dependent. Let's try to do another type of problems. Let's suppose that we know that b1, b2, and b3 are linearly independent. And let's further assume that we know that let's say a minus 2 times b1 plus 3 plus a plus b times b2 plus c minus a times b3 is equal to the 0 vector. Then, since we know that these three vectors are linearly independent, then if we call this x1 and we call this x2 and we call this x3, then we get that for this to happen, we must have that a minus 2 must be 0, 3 plus a plus b must be 0, and c minus a must be 0. Therefore, I can conclude that a must be 2, c must be 2, and from here, b must be -3 minus a, which is -3 minus 2, which is -5. Then if we have this situation, then a must be 2, b must be -5, and c must be 2.